Welcome back to the classroom. My name is Mr. Wong. Today we're going to be modeling projectile motion. We're going to be using a computer simulator to describe different motions that we can see of projectile motion, solve problems using simulators and using Excel spreadsheet to help us perform calculations. And we're also going to do some changing of some variables with our simulator to see what kind of changes in the projectile's motion can we alter in order to get a different outcome in the motion of the object. So let's get started. So let's begin on our explanation of projectile motion. Imagine you have a figurative object in the cannon and you fire the cannon at 10 meters per second at an angle of 30 meters or 30 degrees to the horizontal. Launching height is about 2 meters above the ground. Say we launch the human, and this is how far they traveled over a period of time. We first initially talked about the actual motion of the projectile. So just a quick recall, you can actually see little time intervals of the actual motion of our projectile here. We already said before, if we break this down again, we'll just take this down to 10 meters per second, take it to 30. We already can see that when an object is moving, there is going to be vector components. Okay, any object that is moving in some kind of diagonal motion, we can break it down into little frames to show the individual components, the individual horizontal and vertical components as the object is fired. So let's try this again with the vector diagrams. You can see our velocity components here. Okay, I'll try that again because I didn't actually turn it on originally. So let's try the vector diagrams of our projectile here. You can see the y component was decreasing and it reached a point where it was 0 at the start or at the peak height here. Okay, so let's talk about projectile motion and specifically the vector components. In our first lesson, we talked about when an object is launched at an angle to the horizontal, so it's kind of diagonal, you can think. The diagonal vector will have a vertical component and a horizontal component. So if I fire a cannonball, that's so to say, you can see when the cannonball is fired at an angle, in this case 55 degrees to the horizontal, there is a y component and there is an x component that is influencing the motion of the cannonball. The assumption we make with projectile motion is that there is no acceleration being acted on the cannonball in the horizontal component, that being that we don't see any air resistance. However, for the y component or the vertical component, we do expect gravity to be acting on it. And so what you'll see is over time, this y component will get smaller and smaller and smaller, and then we'll reach a 0 point once we hit the highest point, or what we call the peak height, and then the direction of the velocity will reverse. So instead of going up, it will go down, and then it will increase going down in terms of the speed, as you can see. So at 0 point here, and then it will start going downwards at an accelerating rate. And that kind of describes why the projectile looks like a parabola. So that's a description of demonstrating how projectile motion works. And you can see these little dots here show the individual time intervals of the motion. Now the only reason why this actually works is because even though the object at the peak height has a 0 velocity, it's still moving at a constant rate in the horizontal direction. That's sort of why you can see that the sort of horizontal displacement intervals are equally distanced. The vertical ones, you can see it's really short from this side to this side, but it gets quite large as you go further down because it's to represent that there is a greater acceleration. Okay, so that's kind of what we have there. You can even see the height differentials as you can go from there. Okay, so we're going to do a couple of little experiments. We're going to try and change the overall initial velocity. We're going to try and change the angle of launch. We're going to change potentially also the height in which we launch the cannonball. And using that, and we're going to use a Excel spreadsheet, we're going to try and model the different types of trajectories we'll see, where the peak height will be, and further on also even look at kinetic energy. So let's have a look into that as well. Okay, so what we're going to be testing, the first one, is trip time, or the time it takes for the projectile to be launched from the cannon and then all the way to the landing spot. So we're going to try and change our variables to see what will affect trip time the most. Okay, so as you can see from my little document here, the first thing I'm going to try and change to see what affects trip time will be the magnitude of the launch velocity. Okay, so the first thing, doesn't really matter which angle we use at the start here. Let's just start with 80. We have initial speed of 18 meters per second. Launch that. The total trip time is 3.61 seconds. Okay, so that's just our standard launch at the start. What we'll do now is change the speed. We'll decrease it to, let's say, 10 meters per second. And now let's also compare what the total trip time of the projectile will become. So you can sort of see two things here. One, by decreasing the initial speed of launch, the range or the horizontal displacement traveled by this cannonball is a lot less than this cannonball, but also the peak height has decreased. So you see how this is 4.94. Up here is 16.02 meters. The total trip time was 2 seconds in comparison to this one, which was launched faster at 3.61 seconds. So that's one, or that's actually multiple variables we just tested there. Okay, let's also look at some other variables that we can look at. So we have launch angle. So let's look into launch angle. Let's refresh. So I'm going to alter my launch angle to 40 degrees or 40 degrees. Launch. You can see trip time is 1.31 seconds. Let's increase it. That's 1.67 seconds. So you can see by increasing the angle of launch, we'll try it again, you have increased the total trip time. So you can see that's also increased our trip time here as well. Okay, the next variable we can look at is the acceleration due to gravity. Let's see how that affects the total trip time, peak height, and also the horizontal displacement, and then we'll change the vertical displacement. This I'll explain a little bit later what that means. So on my simulator, there is an option for changing the acceleration due to gravity. I'll make this a little bit faster as well. So this is going to be the range and also the trip time if we have gravity at 9.81. Okay, the trip time, you can't really see that because it's out of range, but this one is 2.09 seconds. Okay, if I increase gravity, so from 9.81, I take it to, let's say, 14 meters per second squared, this is what happens to our projectile. So you can see it decreases the overall peak height. Okay. It decreases the overall trip time and also the horizontal displacement. Okay. When you do an experiment like this, you got to make sure that you are only changing one variable. That's how we ensure that the test is valid. So you can see how all I've done here is change the magnitude of gravity. That's the only variable I'm changing. Not that you can actually change it in real life, but that doesn't matter. The angle of the cannonball of launch is kept the same. The height in which it's launched is also kept the same. So that's kind of the idea here. Okay, so the last one we're going to do is changing the total vertical displacement. So what we mean by that is the height of launch is changed. We're going to do it a slightly smaller value because it's going to be easy to see. It's going to keep the same angle. And we're going to see by changing or alternating this height, how does that affect trip time, peak height, and also horizontal displacement. So the first launch, that's our peak height there. And that's our total range or total horizontal displacement and trip time. I'm going to increase the launching position. You can see that our trip time is slightly bigger. The range is clearly a lot further, and the peak height is also a lot taller. Okay, so that's kind of what you can see by changing these variables around and seeing like that. I'm going to also try and show you using a spreadsheet how you can alternate that and what that can tell us about the energy differences as our projectile is moving along. If you believe this video has helped you understand and validated the different kinematics equations used to describe projectile motion by the way we varied the different variables, give this video a like and subscribe, and I'll see you in the next video where we also analyze this using a spreadsheet as well. Take care.